Welcome all. In this lecture we are going to talk about very simple single input single output control algorithms that are used in the industry. So much so that these algorithms are used on 90% of the controllers that you come across. Of course there are advanced control algorithms, but then they are used for niche applications. So let's talk about these control algorithms. We've been looking at this very simple room example where the heating rate is adjusted to hold the room air temperature by the temperature controller shown here. Now this temperature controller takes in the temperature measurement, compares it with what the desired value of the temperature is, and based on this comparison does a calculation and makes an adjustment to the manipulated variable, which is the heater duty in this case. The calculation is done by means of a feedback control algorithm, which is a quantitative relationship between the MV and the CV. Note that this controller is taking in only, or this controller is basing its move of QHTR only on the value of the temperature as sensed by this sensor. So temperature controller is adjusting QHTR based only on values of the temperature. So in that sense, if we denote U as the signal or the output of the controller is denoted by U, and the temperature sensor is reading is denoted by Y, then the control algorithm gives a quantitative relationship between U and Y. There are some very simple control algorithms: on-off control, proportional control, integral control, proportional integral control, and proportional integral derivative control. These are very simple single input single output control algorithms that are used in practice, and let's just use our common sense and think through these control algorithms and see why they make sense. So if you are interested in holding the room air temperature around a comfortable value of say 25 degrees Celsius, then the simplest thing to do is, if the temperature is below 25 degrees Celsius, switch on the heater. If the temperature is above 25 degrees Celsius, switch off the heater. That's the simplest thing to do, and that's what we do in on-off control. So let's talk a little bit about on-off control. So what we have here is, on the y-axis we have Q heater that is plotted. On the x-axis we have the temperature measurement, and let's say our set point is 25 degrees Celsius. That's the comfortable room air temperature. Now if temperature is very low, that means the temperature is very low, heater is on. If temperature is very low, heater is on. As the heater is on, the temperature will start to rise, so the temperature starts to rise. It crosses 25 degrees Celsius, and as it increases a little further above 25 degrees Celsius, at 25 plus delta degrees Celsius, the heater state switches off. As the heater switches off, temperature which was rising will eventually turn around, and now the temperature will start decreasing. As the temperature decreases, it goes below 25 degrees Celsius, and as it decreases below 25 minus delta degrees Celsius, the heater switches back on. As it switches back on, the temperature that was decreasing turns back and starts to increase, and so you end up in a cycle sort of thing where the heater is switching on and switching off. So the control law is over here. What we are doing is, if temperature is less than or equal to T set point minus delta, heater state is on, heater is at full blast. If temperature is greater than or equal to T set point plus delta, heater is off. In between, no change in state. So what that means, what this intermediate statement means is, if the temperature is between these two limits, QHTR remains wherever it is. QHTR at time t is the same as QHTR at time t minus, just before t. So heater state does not change. So this implies no change in heater state, no change in heater state. If it is on, it remains on. If it is off, it remains off. So this is a very simple on-off control law. If you have a more sophisticated heater where you can set the heater value not just at 0 or maximum, but at anywhere in between these values are accessible, then I can have a more sophisticated control law. And the simplest thing to do is what? The simplest thing is to do is let the valve position or the heater duty be proportional to the deviation away from the set point. I repeat, let the valve position or the heater duty be proportional to the deviation in the temperature away from set point meaning its desired value, 25 degrees Celsius, for example. So here is the proportional control law, and in English what we are saying is, let QHTR be proportional to deviation away from set point. So that's the control law over here. Now if you think about it, some amount of thinking has to be applied, in the sense of, what do you need to do if the temperature is increasing above set point or if the temperature is decreasing below set point. So let us say this is the set point. If the temperature is rising above set point, this is T set point, and temperature is rising above set point, then what do you need to do to the heater duty? Temperature is increasing, so the heater duty must be decreased. So if T set point increases, QHTR must decrease. That's a negative proportionality constant. That means QHTR must be proportional to negative T. So what we are now saying is, QHTR must be equal to a proportionality constant times temperature set point minus current temperature plus a bias term. Why is a bias term necessary? I'll explain that later, but let's just ignore the bias term for the time being and look at this chap. What it means is, let us say temperature goes below T set point. If the temperature is at T set point, then this term is 0, this term is 0 when T is equal to TSP, and the valve position of QHTR is whatever is the bias. So let us say the valve is 50% open, meaning that the bias term B is 50%. Now if temperature goes above set point, this term will become negative, and now QHTR is 50% minus a term, which means QHTR decreases below 50%, which is what you want. If temperature increases above set point, if temperature increases above set point, decrease QHTR. So that is this control law. This gives us, if temperature is increasing above set point, then decrease QHTR. And this subscript T implies valve position at current point in time T, temperature at current point in time T. I am assuming set point of the temperature is fixed, which is what you would expect in a room kind of situation. User sets the temperature set point at, let us say, 25 degrees Celsius. Yeah. Why do we need a bias term? To understand the bias term, consider the situation where everything is at rest, where the temperature is, let us say, temperature is equal to T set point. If we did not have the bias term, let's say this term was not there, then what would we have? We would have QHTR is equal to Kc times 0 when T is equal to T set point. Now at rest, when you wanted on a cold wintry day temperature to be 25 degrees Celsius, the heater, let us say, should be operating at about 50% of full duty, or maybe 40% of full duty. Now instead of QHTR being 40%, what we have is QHTR equal to 0. This implies QHTR is equal to 0 that means when you switch on the controller, QHTR will go to 0, and then the controller will bring it back up to 40% or 50%, whatever is the required value for maintaining temperature at 25 degrees Celsius. That job will be have to done by the controller. So there will be these sudden changes, and this is improper initialization. Improper initialization. If no bias term. Now imagine the bias term is there. You switch on the controller, temperature is equal to T set point, you switch on the controller, and then if you initialize B to be the initial value of T at 0 minus, just when you are switching on the controller. So if bias term is initialized to the value of QHTR at T equal to 0 minus, where time T equal to 0 is when you switch on the controller, then you have perfect initialization, because this term is 0 at T is equal to 0 plus. Bias term is QHTR, whatever is the QHTR value at T equal to 0 minus, and now the heater does not slam shut. So this gives us proper initialization. So the bias term is required for, necessary for proper initialization of the controller. Necessary for proper controller initialization. When you switch it on, because controllers are routinely switched on and switched off. An operator will switch on a controller, let the controller do his job, then he'll say, oh no, let me run it myself, switch off the controller, do his own things, and then switch it back on. These things are routinely done. Proper initialization of the controller requires that the bias term be there, and this bias term needs to initialize to whatever is the value of the manipulated variable when the controller was being switched on, when the controller got switched on. Okay. So this is the control law, proportional control law. I would like to point out, let us say we were looking at air conditioning. Right now we are looking at winter days. Let us say we were looking at summer days. For summer days, summer air conditioning. Now the air conditioning power, or now you have these inverter ACs, what is the speed at which the compressor rotates? Yeah, if you want more cooling, the compressor must rotate at a higher speed. If you want less cooling, compressor rotates at a lower speed. So in these inverter air conditioners, you would have Q cooling. You see, in this case what happens is Q cooling, C for cooling. In this case what happens is, if temperature is increasing above set point, Q cooling must go up. This is what should happen. Earlier what we had in the heater case was, if T goes up, reduce QHTR. Here we have the opposite. If temperature is going up, reduce the cooling. So in this case what we will have is this. There is this negative sign which accounts for this change in control action, and you can see and argue with yourself that this is actually correct. So initially you are at steady state, temperature is the same as set point. Let us say the temperature starts to increase, this term becomes negative, times a negative number becomes positive, and therefore your QC has become B plus something, the bias term plus something. So it has increased. So if the temperature decreases, QC increases. So this would be the correct sense of control. So this sense of control is there. You have to think through what action you must take. If the process variable is increasing above the set point, what action you must take, and that determines the sign of this chap. Conventionally this is called a reverse acting controller. In Aspen Plus or in HYSYS, this is what you say. This is a reverse acting controller. The control action is reverse acting. This is direct acting controller. Yeah. Anyway, we'll stick to our room heating problem. Now let us see the behavior of this control algorithm, and in order to see that behavior, what I'll do is I'll differentiate both sides. If I differentiate both sides, T set point is a constant, this is an initialization constant, so therefore what you get is dq by dt is equal to minus kc times dt by dt. At the final steady state, that means that as time goes to infinity, controller has done all its action and the process has settled at a final steady state. If everything is done right, the process must settle at a final steady state. At that final steady state, by definition of steady state, at the final steady state, what you have is all time derivative terms must be 0. So this should be 0 and this must also be 0. So what you get is 0 equal to 0. So if nothing is changing with time, yeah, this is what you get. The point is, the proportional control law is not imposing any condition that the process variable at final steady state, at infinity, as time has gone to infinity and the process has settled to the final steady state, is equal to the desired set point. There is no such condition imposed by the control law. At final steady state, time derivatives disappear and this equation is automatically satisfied. There is no condition imposed by the control law that the temperature at the final steady state must be the same as the set point. So what this means is, this doesn't hold. T infinity is equal to T set point doesn't hold, and therefore when you are using proportional control, expect an offset away from the set point. So for example, if the set point is, let us say set point is here, temperature is, process variable is also here, you increase the set point. With a proportional controller, the process variable will start increasing towards the set point, but it will never quite reach it. There will be some offset. On the other hand, if there is a disturbance, the set point is over here, there is a disturbance at time t equal to 0, this causes the process variable to go up. The control action will cause it to come back, but there will always be some offset. It does not return back to set point. This is what you expect with proportional control, because the control algorithm does not explicitly impose the condition that temperature at final steady state must be equal to. This condition is not being imposed by the control algorithm. So now let's start thinking, if you don't want offset, what shall we do? That's the question. How do we remove offset? So you start thinking, okay, at final steady state, by the definition of steady state, this must be 0. I also know that at the final steady state, I want this to be 0. So why not? You see, this term must go to 0. This term must also go to 0. Why not relate these two terms and say, why don't we do this? Where what I have done is, I have made the rate of change proportional to the deviation away from set point. Just make these two, just have some proportionality between these two terms. This and that are proportional. So this gives me this as my control law, and I can integrate both sides, separate the variables and integrate both sides. What that gives me is QHTR is Kc by tau I. This is a proportionality constant with consistent units. You see, if you look at the previous control law, if you look at this control law, Kc has units of QHTR divided by degree Celsius. That's the units of Kc. Yeah. Now if you look at this chap, Kc, this has units of Q HTR. You're dividing by time, so you have a proportionality constant. This has units of time. So we are using Kc by tau I, where Kc is the same proportionality constant as similar to for a proportional controller. So when you have this kind of a control law, you will have to have Kc by tau I for consistent units. So you have this as the proportionality constant, and in terms of absolute value of the heater duty, the control law is this, and therefore because of this integrator, it's called integral controller. The manipulated variable value is proportional to the integral of the deviation away from set point until current time. So this is called the integral controller. Now if you look at the nature of this controller, differentiate both sides of this controller. By the way, because of integration, this is the constant of integration. For proper initialization, you again get the bias term. This is called the position form of the algorithm, control algorithm. This is called the velocity form of the control algorithm. but both equations are the same control algorithm, the integral controller. Now if you differentiate the position form, you get the velocity form. So if you differentiate, you go from here to here, and now let us apply this equation at final steady state, at final steady state where t is equal to infinity. After a very long time, process has settled at the final steady state. At that final steady state, this term must be 0, and because this control law must hold, therefore this term must also be 0. So what that means is Kc by tau I is a positive constant. What that means is T set point minus temperature at time t equal to infinity must be equal to 0, which implies the temperature at time infinity is equal to T set point, which implies this. So you see, the integral action eliminates offset. Just very simple analysis shows this. Eliminates offset for a constant set point. So integral control gives 0 offset for a constant set point. Okay. We may combine proportional control and integral control. See, this is the integral term. You could also have the proportional term, or rather this is the integral term. You can also add the proportional term to it. So what you get then is a proportional integral controller. Here is a proportional integral controller where you have the proportional term and the integral term. This is the P term, this is the integral term. So this is called a PI controller. The PI controller is the most commonly used controller in industry. Integral action gives 0 offset, and you adjust integral action using by adjusting tau I, and Kc is used to adjust the speed of response, and we'll talk about this later in the course, but the form of the control algorithm is stated in front of you. And you can differentiate both sides of the equation, and then you'll get dq by dt is equal to dq htr Kc times set point of the temperature is constant minus dt by dt plus Kc by tau I times derivative of integral, they cancel each other, t set point minus t, derivative of a constant is again 0. So this is the velocity form of the algorithm, control algorithm. At the final steady state, this guy would go to 0, this guy must be 0 by definition of final steady state, and therefore at final steady state, because the control law must hold, therefore what that means is t set point minus t must be equal to 0, and this t set point minus t term has come about because of integral action. So again what we recover is that integral action removes offset. So 0 offset due to integral mode in a PI controller. There is, okay, so we have the proportional term, we've got the integral term. How about putting in a derivative term? And how would derivative term be useful? Imagine the same room process, and let us say in the room somebody opens a window. If somebody opens up a window, or maybe somebody is entering from outside and the cold air from outside gushes in, the temperature of the room will suddenly, right, initially the temperature of the room is at set point, but then it drops down very sharply because cold air rushed in. Now as it starts to drop sharply, the error here is small, and if you look at error, meaning this is t set point and this is t, therefore t set point minus t, this is a small number. This is also a integral of this will also be a small number. So what happens is, if there is a sudden rate of change in temperature in the process variable, even though the error is small and therefore QHTR won't move by much, this term is small, this term is also small. If both terms are small, the change in QHTR will also be small. If the change in QHTR is small, cold air has rushed in, temperature is dipping sharply. So what you need to do is make a large correction to QHTR. Now what is it that is large? Well, the slope is large. Even though the absolute value of t set point minus t is small, in the initial period, the slope of t set point minus t, if you look at the slope is large. So the idea comes that, okay, we will make QHTR proportional to the rate of change of, that is the slope, time derivative of the process variable. So that's the idea behind introducing derivative action. So the derivative mode allows action when error is small but process variable rate of change over time is large. And an example that I gave you was somebody opens up a window and cold air rushes into the room. So this is what one wishes to do. You got the proportional term, the integral term, this is the derivative term. In textbooks, this is the derivative term. You'll say, okay, proportional term is this, integral term is this. Let us take the derivative term also to be in terms of deviation away from set point. I prefer to use this because this does not have what is called the derivative kick. No derivative kick. You see, let us say I change the set point. Let's look at this term. If the set point changes as a step, this is set point, then the derivative of set point when the step occurred would be a Dirac delta. This is dt s set point by dt. So QHTR will get this kick because of derivative of a step change. Because here the derivative is not being taken on the set point, there is no derivative kick, and so I prefer this form of the PID control algorithm, proportional integral derivative control algorithm, instead of this. But usually when you talk about PID, you say, okay, proportional to deviation away from set point, integral of deviation away from set point, derivative of deviation away from set point. Okay, so that's why you have this form which has derivative kick. Again, by the way, this is called the error, and if you have a process system where you have the control input and you have the process output y, error is deviation away from set point, and so for the general case where the process variable is represented by y and the deviation away from y set point is represented by e and the manipulated variable is represented by u, the position form of the PID control algorithm is this guy. This chap here. This is the proportional part, this is the integral part, this is the derivative part, and of course the bias is required for proper initialization. So this is the PID and control algorithm, and 90% of the controllers in industry you will see are of the PID type. Kc, tau I and tau D. Kc, tau I and tau D, these are tuning parameters that the control system designer or the controller designer must adjust properly so that the controlled process exhibits a dynamic response that you want. So Kc, tau I and tau D are tuning parameters. These are tuning parameters that the control system designer must choose properly so that the system gives the desired response under control, so that you bring about the desired change in the dynamic characteristics of the uncontrolled process. Okay. I just did some simulations, and maybe what we will do is the first lab will be simulation of this room example. Initially the room is cold. Right now temperature in Punjab, Haryana would be, minimum temperature at night would be 0 degrees Celsius. So let us say the temperature is 0 degrees Celsius of the room air. Everything is off. And then you switch on the heater, or you switch on the controller, and you could have on-off control, you could have proportional control, you could have integral only control, proportional integral control, or you could have PID control. So what's plotted in the figure are responses for the different types of control algorithms, and what you see is with on-off control, you can see as you switch on the controller, heater duty goes to maximum, stays there. In response to that heater duty going to maximum, temperature starts to rise. It exceeds T set point, and as it exceeds T set point plus delta, the heater is switched off. The heater temperature continues to rise before turning back around, and then it goes below T set point minus delta. I think I used a delta value of 0.5 degrees Celsius. I don't remember exactly. The temperature continues to decrease before it turns back around because the heater has switched on, and then the temperature rises, increases above set point, heater switches off. As heater switches off, increasing temperature turns around, decreases below set point, and the cycling continues. So what you have is, if you use on-off control, you get this typical cycling behavior. Process variable is cycling, and the manipulated variable is bang bang, switching on, switching off, switching on, switching off. So bang bang control, that's on-off control. If you put in a proportional controller, then what happens is, the proportional controller is this blue dotted line. Again, the heater switches on, maxes out at 100%. In response to 100%, temperature rises as before, and then after a while the controller moves away from, as the temperature approaches set point closely, the heater duty starts decreasing and temperature oscillates a little bit and settles. But then you see there is this offset. The final value at which the temperature settles is not 25 degrees Celsius, it's maybe 21 or 22 degrees Celsius. Yeah, so there is this offset with proportional control. If you use a PI, an integral only controller, I only controller, the integral action takes the temperature very slowly towards set point, and if I had simulated it for further time, 150, 200, 300 minutes, you would have seen that it actually settles here. But then the control action is very slow. If you try to increase the integral action, you will see you start getting oscillations. So to avoid oscillations, you have to use, you cannot use too much integral action, and therefore the response is slow. PI, PID control, the responses are shown here. The black curve is PI, the red curve is PID. You can see the PID control, red curve is slightly above the black curve, and so control of the process variable is slightly tighter with PID control. But you can see PI and PID are similar responses. And you can also see that there is no offset in the response. Integral action I only controller shows no offset. PI and PID control give much faster response with no offset. Yeah, so these are the kinds of responses that we get using our very simple control algorithms. On off, proportional, integral, proportional integral, proportional integral derivative. Now if you make a change in the temperature set point, so I've just simulated the case where initially the process is at steady state, and then at time t equal to 0, set point is changed from 20 to 21 degrees Celsius. And then you can see PID control for the tuning that has been used. The control is really tight. You get very close to set point quickly and settle down, whereas PI control is the red curve. The control is slower. You reach the set point slower. You have a larger overshoot, and then settling also takes somewhat longer. So PID control gives the fastest response, where you settle to the set point quickly. Of course, this fast response comes at the expense of more aggressive movement in the Q heater duty. Yeah, and you can see the blue dotted curve, proportional only, there is an offset. So PI and PID no offset. PID allows you more aggressive control. So if you choose your tuning parameters properly, PID control gives the tightest control amongst the three variants. Okay. More complex control algorithms are possible. There is the feed forward idea. What is the feed forward idea? Let us say you find out that a cold front has come and the temperature outside has suddenly dropped. If the temperature outside has suddenly dropped, you know that the room air will get colder because of more heat loss, because outside air has become very cold. If you know that the outside air has become very cold, what you can do is increase the heater duty slowly, and this increase in the heater duty will counteract the expected decrease in room air temperature because of the colder outside air. This is the feed forward idea. You know a disturbance has occurred, you have a measurement of the disturbance, and so to counteract that disturbance, you change your manipulated variable so that the change in the process variable is equal and opposite to the change expected due to the disturbance in the same process variable. So the control action counteracts the effect of the disturbance on the process variable. So this is the idea behind feed forward control. And of course, for feed forward control, you need to have a model. What is the expected change in the process variable temperature due to a step decrease in the outside air temperature? Okay, so if the outside air temperature decreases like this, what is the expected change in the room air temperature? Or let's say this is room air temperature. Room air temperature is going to decrease like this. Let us say this is what I expect. Now if I can increase my heater duty so that the heater duty changes equal and opposite to what is here, mirror image about the time axis, if it changes like this, this is not a mirror image, but anyway, supposed to be a mirror image. So this is expected response due to disturbance, and this is the disturbance. So expected change in temperature due to the disturbance. If I can change my u such that Tu is equal to minus Td, then when I add these two up, the actual change in the process variable is 0. So the process variable stays undeviated from its set point. This is the idea behind feed forward. And to implement feed forward, you do need an expected response due to the disturbance. A model of the disturbance is necessary. Also, a model of the effect of the manipulated variable on the process variable is necessary. So you need a model of both disturbance effect on the process variable and control input effect on the process variable. So the principal idea is to counter the effect of a measured disturbance by appropriately adjusting the manipulated variable. The adjustment in the manipulated variable must be made in such a manner that it counters the expected effect of the disturbance. Of course, the disturbance must be measured. Otherwise, you don't even know whether the disturbance has occurred or not. You need dynamic models of both how the MV affects the CV and also how the disturbance, the measured disturbance, affects the CV. So major correction is via feed forward, and of course if your models are not perfect, the CV will not reach the set point. Those minor deviations can be corrected for by using a PI controller, a feedback PI controller. So major correction is via feed forward, model based. Minor correction is via feedback. You could also have model based control. Major correction is again via model. Feed forward and model based control are very similar actually. Minor correction is via feedback. Model based control and feedback is actually how we all operate. Take any example. Let us say you have a singer singing. The sur changes, the changes in notes and the rhythms, that template is there in the mind of the singer. He or she follows that template as closely as possible, and he's also listening. And if you are slightly away from the exact note that you want to reach, feedback allows you to correct. So major correction is using the model, the training that the singer has. That's the model of notes that the singer has in his or her mind. So you get close to the note using that practice bank that you have in your mind, that model that you have in your mind through the hours and hours of practice that you've done, and then hitting the exact note at the right time. That is done through feedback. Yeah. So major correction via model, minor correction via feedback. So you have these concerts. In the concert, singers and performers will have their monitors in front of them. That those monitors are there so that they can hear what they are playing, and that's the feedback part. If they can't hear what they are singing or playing, they will go off note. If not initially, later on, because they can't hear what they are playing. So feedback plays a major role, but of course practice and the model of what needs to be played, that also plays a major role. Now you can see on-off control was very simple. Nothing. So heater is on if the temperature is below set point. If the temperature increases above set point, switch off the heater. Just on-off. Very simple, primitive. But then this primitive control algorithm causes a sustained cycling limit cycle. It's called a limit cycle. You use a proportional controller, and now you need to access intermediate values between maximum heater duty and 0. So your equipment will have to be a bit more sophisticated. But then proportional control results in offset. You can expect offsets. So you say, okay, we'll implement integral action. Your controller is becoming more complicated. In the on-off controller, all you need to do is specify the set point and be done. The set point is there specified in all controllers, but now with a proportional controller you got to figure out what Kc should be. With a pi controller you need to figure out what Kc and tau I should be. And if these are figured out properly, you get a good dynamic response with no offset. With a PID controller, you need to figure out those three parameters, Kc, tau I and tau D. So the complexity is increasing. Simple control systems will give you more robust control, but the control will not be very tight. As you start increasing complexity of the controller, Kc tau I, tau D, feed forward ideas, model based ideas, the control algorithm or the control calculation becomes more complicated. The more complicated the control algorithm, the more fragile the system, because you may not have tau I right, you may not have tau D right, or you may not have Kc right, one of the three. Yeah, values may not be right, and that compromises the control performance. So in order to extract benefit due to the additional complexity in the control algorithm, you need to know exactly what kind of a model to use, how to tune the controller, what is an appropriate tuning, what is not an appropriate tuning, and so on and so forth. So control benefit comes at the expense of increased complexity, and if you don't harness the complexity properly, you may also end up in a situation where the more complex control algorithm actually performs poorly, and then you say, oh, the model was not right, oh, my tuning was not right, oh, maybe there is a non-linearity in the process system that my model does not account for. All these kind of cock and bull stories you start getting. Yeah. So complexity versus simplicity. Make the control system only as complex as is necessary, because simple is robust, complex becomes fragile. So when you have a complex control algorithm, you can get tight process variable control, but the system is very fragile. Now let's look at some ideas. Person is balancing this bike. The balancing act, is it feedback, feed forward, or model based? Think about it. Person knows how to balance the bike, and now he's riding on a road, and he makes sure that he stays on course and avoids all traffic. Is it feedback, feed forward, or model based? Think about it. Wading through traffic, is it feedback, feed forward, or model based? Objective being you don't bump into each other, you don't hit another vehicle or person while going in the direction in which you want to go. Is it feedback, feed forward, or model based? Driving on a highway, feedback, feed forward, or model based? Near exact grocery weighing, feedback, feed forward, or model based, or a combination? Fine tuning of guitar strings, where the guitar string sounds exactly right, is it feedback, feed forward, or model based? Just ask these questions to yourself and answer them. Balancing a stick on your palm, so in summary, process variable feedback based adjustment of the manipulated variable is a powerful means for control. Common CISO feedback control algorithms are on-off and PID. PID is the most commonly employed industrial control algorithm. In fact, in the process industry, more than 90%, don't be surprised if more than 90% controllers are PID, simple PID, which were invented at the turn of, in the 1900s, early 1900s. Integral mode gives offset-free control. Derivative mode allows accelerated or more aggressive manipulated variable adjustment. More complex algorithms are possible, feed forward plus feedback, model plus feedback. However, these complex algorithms should only be used only when absolutely necessary. One should prefer simplicity over complexity always, because simple is robust, complex is fragile. If you and you will see this even in human beings. Simple people are generally happy people. They don't think too much. They'll be trusting in nature. Of course, they'll be taken for a ride, but in general, they are trusting in nature and they are happy with whatever life offers them. Those who think too much, you know, those guys, they are never happy. You give them the whole world and it will still not be enough. Yeah. So simplicity versus complexity. Simplicity is something that one should prefer always. Things should be made only as complex as is necessary and no further. Yeah. With this, we come to the end of this lecture. Thank you for your attention. Good day.